Let's carry on looking at some sets in R2 before we move on to R3, just to get used to working with set builder notation. So maybe we'll look at the set of, and I'm going to switch from x1, x2 to xy, just because it's a little simpler, a little lighter on the notation. So all xy pairs, and let's say x plus y is bigger than or equal to -1. All right, so it's usually easiest to understand the region by first figuring out what the boundary is. So we look at x plus y equal to -1, and that will tell us, let's see, that's going to be this line right here. And if you don't see that from the form that it's written in right now, you can just rewrite this as minus x minus 1, so it's in mx plus b slope-intercept form. And then again, the best way to figure out if you're on the right or left side of this line is you pick a point that's nice and easy to compute, like 0, 0 is often a good example. And then you can check and say, okay, so if I go back to that inequality, is 0 for x and 0 for y, does that put me in the set? So is this a true statement? And the answer is yes. So that means that point is in there. So the set I'm looking at, D, is this one over here. We could do, let's take E to be the set of all xy pairs in R2 such that x is less than y squared. All right, so then we need to draw that. So again, let's look for the boundary. So x equals y squared. So that's the same thing as positive or negative root x is equal to y. So we see we've got a sideways opening parabola, and it's going to be something that looks like this. And let's see, I need to pick a point to figure out if I'm in there or not. So this one right here, this is where x equals 1 and y equals 0. So if I do x equals 1 and y equals 0, then that point is not in there. So I'm going to say that it must be this region out here. So there's my set E. Then let's see, moving on to let's do another example with circles. Now this is where we're going to have two sets. We're going to look at a shape that's formed by the intersection of two regions. So we're going to look at a shape that's the intersection of two regions. So let's take F to be all the x, y pairs in R2, where x squared plus y squared is less than or equal to 1, and y is at least 0. So now this and here means intersection of regions. Sometimes this is denoted with an upside down U symbol for intersection. So that means that I'm looking for the points that satisfy both inequalities. And so let's see, so for the first one, I have the points inside the unit circle as we saw before. Oh, wait, but it's inclusive because it's a non-strict inequality. So we have, so this part here corresponds to that guy. And then over here, I'm looking at this upper half plane, right? Everything up here, that's what corresponds to this inequality. And so the intersection of these two regions is going to be all of the stuff that's in the circle and in the upper half plane. So this region up here. So that's going to be my set F. Before we go on and do something from R3, I just want to show you another way to use set builder notation, which sort of shows or alleviates a redundancy. And that is, I could also say, let's see, so in a previous slide, we used the idea that A was actually this upper half plane right here. So I could have written that f is equal to all of the xy points in A such that x squared plus y squared is less than or equal to 1. And so this is how you see the flexibility of set builder notation. This part here doesn't have to be Rn. So for subsets, that's sometimes helpful. Okay, let's go on and do something from R3. So I'm going to take, I'm going to go back to reusing the letter A. So we'll take x, y, z now in R3 to be where y is non-negative. Okay, so this is the same inequality that we saw just above that gave us the upper half plane. But now that we're in R3 and we have a three-dimensional coordinate axes here, this one's our y-axis, the plane y equals 0 is this one right here. So this is y equals 0, also known as the xz plane because it's spanned by the x-axis and the z-axis. And so now we're taking y to be non-negative. So that means that we need to include this plane here that contains, so this is where y is equal to 1. And then this next plane out here, this is where y is equal to 2. And I said next, but actually it's everything in between, right? So I want to take everything that extends to the right from this plane, and this includes everything going all the way up and all the way down. I just drew it like this square to sort of visualize it, but it's an infinite plane. It's got no boundaries. Okay, so we get this half plane, a half space, the right half space, everything on the positive y side. And similarly, let's see what happens when we take something like all x, y, z triples. And earlier when we did x squared plus y squared less than or equal to 1, we saw, we did it strictly less than 1. We saw that that gave us the inside of the unit disk. So now the thing is, we're in R3 now, but there's no constraint on z, the vertical coordinate. So that means we can visualize it anywhere. So for example, I could say, what does it look like if we look at z equals 0? Well, z equals 0 just doesn't come up in this inequality, so we can just plot it and say, oh, okay, so in the xy axes, it's going to be that disk. All right, well, what if we looked up here at z equals 1? Well, then again, we're going to have, let me draw the little axes on there. It's going to be the same thing. It would just look like that same disk, and changing the value of z does not change the figure at all, simply because z does not occur in that formula. So that tells me I'm going to have the same copy of this unit disk no matter what height I go at. Or in other words, the absence, and maybe take a note of this, the absence of z in that condition means that it's unconstrained in the z direction. So all of these points all the way up and down are going to be included in my set. So B here is an infinite cylinder. Goes up and down forever, and it's open, so it doesn't contain its boundary because of that strict inequality. And maybe one last example. Let's take C to be all the points that satisfy x squared plus y squared plus z squared, now bounded by 1. And this one you probably recognize from x squared plus y squared plus z squared equals 1, the boundary, that the region that we're talking about here is the unit sphere. And we'll talk more in the forthcoming videos about, and it's the inequality, so we're talking about what's inside it here. And we'll talk more in the forthcoming videos about how to see that this is a sphere and recognize it and graph it.